Hello everyone, my name is Uttam Biswas and I'm currently pursuing MTech. I'm taking CICPS. Today I'll be presenting my course project for DA623 titled Multimodal Sentiment Analysis. So, this project explores how we combine multiple data modalities like text, audio, and video to better understand human sentiments. So, let's begin. So, here's the second slide. That's motivation. Why multimodal sentiment analysis, basically. Uh, in real life, when humans interpret emotions, we don't rely on just text. We use a combination of textual information, tone of voice, and facial expressions. That's multimodal by nature. In today's digital world, think of platforms like social media, video conference, or even YouTube comments or live streams. Communication happens through multiple channels simultaneously. So to truly understand sentiments in such scenario, we need systems that go beyond just text. And this has real world relevance, like content moderations, which can detect toxicity more reliably, virtual assistants, which can respond empathetically if they understand emotions. Customer feedback analysis becomes more insightful when tone and expressions are factored in, not just the words. Historical perspective. There, in historical perspective, I wanted to show the two approaches. One is the early approach, and the other one is a deep learning approach. What is this early approach? Basically, in early approach, in initial days, each modulator like text, audio, and visual was handled uh, separately using handcrafted features. These features were fed into traditional classifiers like SVMs or decision trees. Fusion happened only at the feature level, often resulting in weak integration modalities. But with the rise of deep learning, we enter into a new era where benchmark datasets like uh, CMU MOSI or CMU MOSI the become available, making large scale multimodal results possible. Deep architecture like LSTMs, TFNs allowed us to learn joint parameters from multiple modalities. This model significantly improved the alignment and integration of multimodal corpus, giving us better performance and more neutral emotions recognition. Transformers in multimodal uh, sentiment analysis. Uh, Modern architecture like Mayolt, Plaba leverage attention mechanism to fuse different modalities such as text, vision, and audio in more dynamic and context-aware manner. This allows us for better alignment and integration across modalities compared to older fixed fusion techniques. More importantly, these models are part of large trend toward unified multimodal models, which aim to process all modalities in a single end-to-end framework. Coming to next is learning from the project. What I have learned from this project is that uh, I explored multiple research papers for this project, and I finally come into this research paper, which is Tensor Fusion Network for Multimodal Sentiment Analysis by Jades and Fourier, Cambria, and Morrissey. This stood out for its innovative approach to modeling intermodal interactions. It introduced the idea of explicitly capturing unimodal, bimodal, or and multimodal, trimodal dynamics using a tensor-based fusion mechanism. Why this paper? What made TFN special? It goes beyond text to include speech tone. It just not only work with text, it works with speech and facial expression as well. Focuses on intramodality dynamics and intermodality dynamics. So what is intramodality dynamics? It tells us how patterns evolve within each modality over time. And what is intermodality? Is that how modalities like speech and facial cues work together to convey meaning. Abstract. What the paper says. Sentiment analysis is equals just more than just text. It's not just a text, it's more than just text. And TFN learns from patterns within and between the modalities. It's not only learn from text, it learns from text. It is correct that it learns from text, but it also learns from text within their modalities, like from text to audio, fusion, or text to video fusion and things like that. It is especially effective on video data because expressive there you can see the expression, tone, and the gesture. And again, you can also hear the voice as well. So outperforms past state of art models. Introduction. Now coming to the introduction part, what exactly is multimodal analysis? Uh, what is multimodal sentiment analysis? Is that it goes beyond text. It not only just gathers uh, text, it includes voice and visual spatial expressions. Focus understanding the emotions within the video. And it generally helps in learning sentiment from videos, uh, such as from YouTube videos, from Facebook. So it is important in today's world because we're filled up with lots of videos around us and lots of social medias around us. So videos are nowadays are very easy to get, and to understand sentiment analysis, not just by text, it is very vital for us to understand it through video as well. Why is it hard? Challenges is multimodal sentiment analysis. Why is it hard? Because it is not the same sentence doesn't convey the same sentiment. Sentence with a smile and another with a frown expression, both have different contexts. Uh, and we can understand this context from the tone and expressions. And speech can also be messy. Like whenever we speak, we just do not speak we do not speak speeches, we do not give speeches in a fluent manner. We may give speeches in fluent manner, may not give speeches in fluent manner. We might have pauses, we might have repetitions, we might have our tone shifts due to various reasons. So it is basic. Early fusion versus late fusion. There are two common strategies for to multimodal, we can say. Early fusion, where we combine features from all modalities right at the beginning before putting them into the model. While this allows for interaction across modalities early on, it is also causes an overload of information, which can be difficult to model effectively, especially when modalities are noisy or unaligned. In contrast, late fusion keeps the modalities separate during learning. Each modality gets its own model and then the outputs are combined in the end. This is easier to train, but comes with a cost. It often misses the interactions and causes modern dependencies, which are critical for understanding emotions. The Tensor Fusion Network, TFN. Again, TFN learns intermodality dynamics, which I speak about in the slides before previous one. So it uses tensor fusion, which captures all possible combination of the modalities and has a networks for each input like text, audio, visual, for speech, audio, for visual is video, and there's text as well. Why TFN works? Because provides better results with fewer assumptions. It works well on complete video. And complete video means that it works well with a video, which have text, which have expression, all of it in a same play, and it works well with it, and it still performs strongly even when even when it is asked to work with single modality like text or with visual or speech. So it outperforms basically earlier every fusion strategy. Then comes why multimodal matters. Why multimodal fusion is essential in a way. Let's consider the phrase where we can see in the diagram the movie is sick. It has different kinds of we can give different kinds of tone to it. We can give different kinds of visual to it, and we can have different kinds of output from it. So in a unimodal setup, say only the text, the movie is sick. we are often left guessing. We become our sentiment gets confused because what it is. The sick can also be very negative. The sick can also be very positive as well. So then comes bimodal, where bimodal takes a text and the uh, text and a facial expression. Let's say. So the movie is sick with a smile. If a person is saying the movie is sick with smile in his face or in her face, then it will definitely mean that he or she is excited about it, and it is a positive sentiment. The movie and again the movie is sick with a frown expression in his or her face. That means that that movie was not that good, and he or she is very disappointed. It is a negative sentiment. And if we have, again, if we have the movie sick with a loud voice, we may or may not get guess correct sentiment because she or he might be very much excited, and so she or he was using loud voice. Or again, she or she might be very much uh, angry about the movie that she or he was very much loud about it. So then there comes trimodal, where we use three modalities in together, like speech, expression, and the sound. So if we use three of them, we can definitely get a sentiment. We will not get into a confusion state. How sentiment analysis evolved. It first started with text, and then based on words and sentences, we started to analyze sentiments. Then it shifted to video platforms. So there we needed multimodal approaches. Now we have text again, speeches again, text tones and visuals for better understanding. Now we use CMO, MOSI, and deep learning model. So basically, these are the two data sets. These are two data sets. And for this project, I use CMMSI, so which is a popular dataset of spoken videos with emotion labels. Uh, Deep learning models are like CNNs, LSTMs, SVMs used for fusion. So CNNs can be used for visual data, LSTMs can be used for audio and text as well. And again, in some cases, even traditional classification SVMs for comparative evaluations. It focuses on language, speech tone, and facial expression. Again, connection to emotion recognition. Beyond words are emotion recognition. Uh, Sentiments are like positive, happy, positive, negative. These are neutral. These are the sentiments. Uh, so it is very much deeply connected with the broader field of emotion recognition. What sentiment analysis typically looks at positive or negative opinions, emotion recognition aims to reflect specific emotional state, like happiness, anger, sadness, using facial gestures and voice tone in addition to speech. So this aligns with the multimodal trend we've discussed, and it basically helps in human-computer interaction, virtual assistants, mental health apps, etc. etc. CMU MSI data set. What it is a real world multimodal data set, a data set of short video clips with movie reviews. It has been collected from YouTube. Again, it has been collected from YouTube, which means the content reflects real world unscripted behaviors. And again, annotations have includes text, audio, visuals. CMU MOSI dataset include details. So, what are inside the datasets? There are 2,199 level opinion clips from 93 different speakers covering varied demographics. Level ranges from high range, which is plus 3, from highly negative minus 3 to highly positive, positive 3, plus 3. So, average is 23 clips per video, and each has 4 seconds, each videos per 4 seconds in average. What is TFN? TFN is a deep multimodal architecture designed for spoken sentiment analysis. It just not works with text, it works. It combines all text, videos, and visuals and audio modalities, text, visual, and speech acoustic modalities. And then it learns not only their individual patterns, but also the combined cross model interactions. TFN architecture structure. TFN structure uh, architecture of TFN into its three. Let's break down architecture of TFN in its three. Uh, those three main components. One is modularity embeddings of networks, which learns basically each modulated text, audio, video passes through its own subnetwork. These subnetworks are modularity specific feature and produce dense vector. Tangent fusion layer. This is core innovation of TFN. It applies a three-way Cartesian product across the embeddings of three modulators to explicitly model unimodal interactions, bimodal interactions, and trimodal interactions. This what TFN doesn't miss any possible cross-modal dynamics. Sentiment inference subnetwork. Finally, a fused transsensor representation is passed to this subnetwork, which either classifies the sentiment category or regresses a continuous sentiment score. Why tensor fusion? Traditionally, early fusion methods just concatenates the features from different modalities. While that's very simple, but it completely misses out the rich interactions between them. It misses out the rich interactions that can exist between the modalities. Tensor fusion captures text, voice, nuisance, like sarcasm or excitement that comes through tone, facial expressions, face tone alignment, like smiling while speaking softly versus loudly, cross-modal sarcasm. It also helps model complex behaviors like cross-modal sarcasm, emotions, and emphasis. Output options. Depending on the use case, the output of a sentiment analysis model, including TFN, can take different forms. Binary classification. This is simplest setup. The model data is whether the sentiment is positive or negative. That's it. Multi-class classification. Here, sentiment is broken into multiple categories. For example, ranging from very negative, high negative to high positive. Regression. In some cases, we need a real valued sentiment scored like a number between 3 and minus 3 and plus 3. Spoken language embedding subnetwork. Modeling modeling spoken language. Okay. Unlike written text, people speak with lots of pauses, filters, and fragmented expressions like things like yeah, okay, no. So we need a model that focuses on meaningful parts and removes these noises and tracks context. So we use two-part strategies. First, we apply globe embedding for converting it into dense vectors. Then we feed these vectors into LSTM, a type of recurrent neural network that's very good at modeling sequential data and capturing context over time. This is the LSTM architecture. Figure 3 showing as figure 3 is the spoken language embedded subnet architecture, where each word in the sentence, if you like, and dot 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 C is first converted into dense vector. So using glove embedding. Then these vectors are passed through sequentially through an LSTM layer, which understands the conceptual dependencies across time. And the outputs of the LSTM are represented as H1, H2, H3, dot dot to so on, where each represents the hidden state at a particular timestamp. These are then passed through the two ReLU activated dense layers to form the final embedding JADR, which represents the sentence level language feature. And on the right side, we can see that that is the mathematical formation of the LSTM. Final output of the spoken language subnetwork. This is final output, JETL, language embedding. So this is how it is calculated, where R128 is showing that it is a 128 uh, dimensional vector. This vector captures both semantic meaning of the words and contextual information over the sequence. Visual embedding subnetwork. So the model analyzes the speaker face model. What it does, it models facial cues from videos. Speaker faces are analyzed frame by frame in 30 frames per second, which provides fine-grained temporal information. It extracts facial features using facet, which provides emotional probabilities and action unit activations, helping us detect subtle expressions like a frown or a smile. Then there's another strategy. Uh, then there's another tool that is OpenFace, all crucial for interpreting non-OpenFace, which captures head pose and landmarks and face angles. Features are average across prompts. One vector is V. So this is visual embedding formula Z to the V, where combined visual vector V is fed into neural network, three-layer neural network, each unit having 32 value units. This step allows the network to non-linearly transform the raw visual cues into a more compact and meaningful representation. This is acoustic embedding subnetwork. Acoustic embedding subnetwork. Uh, it captures emotions from voice. To use it, we can use copper Wave toolkit to extend voice features. First, it includes MFC. Feature expression include MFCs, which captures the spectral properties of speech, each indicating the tone variation, voice or unvoiced frames, and inverse. And there are some advanced features as well, like glottal flow and pitch slope, which relate to vocal effort and step. These features are sampled every 10 milliseconds and providing a fine-grained temporal resolution of how voice changes over time. Uh, Frame-wise features are then again average into a vector A. This is the formula, acoustic feature to embedding ZA. And again, it is same as the last one, where it is passed through a three-layer feed-forward network, on each hidden layer having 32 value units. And this is the formula for it. Tensor fusion layer. Tensor fusion layer, TFM. What makes TFM different? Standard fusion, what it does is it concatenate. So it misses deeper interaction. Tensor fusion captures unimodal, bimodal, trimodal relations. It combines modalities. That's it. How tensor fusion works? How tensor fusion works? First, uh, we can take each modality embedding language, JET, visual JET, V, and acoustic JET, and append a constant to append a constant one to each vector, which then make JETL to become a vector in R129, jet V become a vector of R33, and jet A become again vector of R33. Then we perform outer product of these vectors, this which results in a high dimensional vector, 3D vector. The tensor encodes every possible interaction, unimodal, bimodal, trimodal. So rather than collapsing everything into a single fused vectors too early, this approach retains the structure of multimodal interaction. Fusion without extra parameters. Uh, Unlike typical neural layers that requires wet matrices and training, the fusion tensor is constructed using fixed outer patterns. So the structure of the interaction is learned purely from the input representation. And yet, TFN still performs well thanks to its uh, structured representation of modality, combination, and its ability to meaningful cross-modal interactions explicitly. This design has two major advantages. First of all, it helps avoiding overfitting and it keeps the model lightweight. Early fusion versus tensor fusion. You can see the left diagram where early fusion does that. What it's just stacks modalities. It just stacks modalities. And the tensor fusion captures complex representation. It has fusion, combines modalities. It combines modalities. Sentiment inference subnetwork. So after generating the fuse transfer, like final sentiment prediction, it takes a fixed fuse transfer from previous layer, suppose, and we passed it, pa- it the fuse transfer is passed through the sentiment inference subnetwork. This is where the actual sentiment prediction happens. It's a compact two-layer neural network designed to be efficient yet expressive. This network reads the least fuse features and outputs a sentiment prediction. Depending on the task setup, this prediction can differ in forms: binary, positive versus negative, 5+ classifications, very negative to very positive, and then there's comes scores as well. Experimental setup, testing the TFN model. So model comparison. Three major experiments were conducted. Model comparison, where it compared the TFN model with all the previous best methods. Ablation study, check contribution of unimodal, bimodal, trimodal parts, and yield division was a TFN. What it is saying that in this study as well as different parts of the model to check the individual input. For example, what happens if we remove trimodal terms and we use only bimodal or unimodal parts? How does early fusion compare to tensor fusion? Um, So these insights will help us understand which design decisions truly contribute to performance. Single modality performance, how well each modality works alone. Experiment 1. In the first experiment, we evaluate TFN across three tasks: binary sentiment classification, 5+ sentiment classification, and sentiment regression. TFN achieved the highest accuracy in both binary classification and 5+ classification, as you can see. In binary classification, it gets 77.1%. In 5+ classification, it gets 42%. And it also represented the best regression performance with ME, mean absolute error, as 0.87 and Pearson's R is 0.70. It outperforms CMKL, the prior state-of-the-art kernel-based method, SLCNN, a bias-aware model, CNN model, as well as traditional models like SVM, and render bias. Importantly, TFN narrows the gap to human level accuracy, especially in binary sentiment classification. In experiment 2, we conducted an ablation study to understand how different components contribute to TFN's performance. Yeah. So here are key takeaways from this experiment. TFN language is strongest individual modality. Again, bimodal combinations outperforms to the full trimodal in some cases, but both are significantly better than using the single single modality. When you remove the trimodal interaction terms, TFN trimodal, performance drops, showing that all three modalities working together each adds value. Working together adds value. TFN also outperforms early fusion. Experiment 3.1, where we compare TFN language, that is using only the language modality from TFN, against several state-of-the-art stacks only sentiment models. TFN language achieves 74.8% accuracy binary in binary uh, experiment, 30.8.5% accuracy in 5+ classification, 0.98 MEE and R as 0.62 in regression, and it beats RNTN, recursive neural transfer network, DAN, deep averaging network, and DCNN, dynamic CNN for text patterns. It handles spoken language better than models trained on written reviews. It is better likely because it handles better because uh, likely because it's trained on actual spoken utterances, unlike traditional models that are often tuned for written reviews. Then comes 3.x2 experiment where TFN visuals are compared with facial expression models. For TFN visual achieves 69.4% accuracy and with along with 71.4% F1 score in binary classification, 31% accuracy in 5 plus classification and 0.11 to MER R and S 0.50 in regression. It outperforms 3D CNN, CNN LSTM, LSTM FA, temporal vision models. CMKLV and SLCNN CNN are multimodal visual fusion models and it outperforms them as well. One strength of different visual is its ability to capture subtle expressions such as micro expression or blended emotion. In experiment 3.3, we evaluate the performance of TFN acoustic with page pairs models. So here are the highlights of this experiment. Acoustic model TFN acoustic achieves accuracy of 65.1%, along with F1 score of 67.3% in binary classification, 27.5% accuracy in 5 plus classification, and 1.23 ME and R is equal to 0.36 for regression. It outperforms HLRNN, which models prosody features, EduNet, which processes raw audio waveforms, SER-LSTM, which uses spectrograms, again, and CML, KLA, SAL, CNNA, SVM, MDA, all of which are multimodal models similar to acoustic inputs. Here we shift from numbers to qualitative analysis to see how TFN behaves in real-world composition settings from the CMO MSI dataset. So, for first example, you can say you can't even tell funny joke with a frowning expression. The speaker is frowning, and although the text may seem ambiguous, TFN visually detects strong negativity unlike the other models. I give it a B plus smile expression plus excited voice. This is example 2. Here TFN correctly predicts this strong positive statement. Even though the sentence is short and vague, the combination of smile plus tone made the difference. Example 3 we can see, but I must say those are some pretty big shoes to fill, so I thought maybe it has a chance plus H share. TFN correctly predicts a neutral sentiment, you can say, showing it can resolve cross-modal contradictions. The only actor who can really sell their lines in Erin Eckert plus Brown plus low energy voice. So TFN and TFN acoustic both predict correct negative statement thanks for capturing tone plus emotion. Thanks to capturing tone plus emotions. So to conclude, the TFN presents a powerful and elegant way to model interaction across multiple modalities, language, visual, and acoustic, making it ideal for tasks like sentiment analysis. On the CMO MSI dataset, TFN achieved a state-of-the-art result across binary, 5 plus, and regression settings. Unlike earlier approaches, TFN doesn't just combine modalities, explicitly models unimodal, bimodal, and trimodal dynamics, leading to richer, more accurate presentation. It also demonstrates that deep multimodal learning can be both interpretable and verbose, offering practical values in areas like social media analysis, human-computer interactions, and emotion-aware AI. This is the reference I've used for to present this paper, present this slide, present this presentation. What surprised me in this project? So, first of all, I didn't expect TFN to outperform early fusion by such a wide margin. And the fact that explicitly modeling intermodality dynamics can make such a big difference really stood out to me. I also found it fascinating how much visual acoustic cues help disambiguate text. Finally, I was impressed by how well TFN performs even in unimodal settings. Uh, Scope for improvements. Uh, while the TFN is very much effective, there are still several areas where improvements can happen. First, the fusion transfer is high dimensional, which can be computationally expensive. Supplying low rank approximation can help reduce its size and efficiency. Second, TFN assumes that all the modalities are always available, making it robust to missing or noisy modalities, would improve real world usability. Third, TFN uses LSTMs for temporal modeling, but newer architecture like transformers could capture longer dependencies and complex interactions more effectively. Another direction is to extend the model from basic sentiments to fine-grained emotional analysis, such as identifying joy, anger, or fear, which would have been broader application. However, and finally, testing TFN on longer, more diverse datasets would help verify its generalizability beyond CMI MSI. So while TFN sets a strong foundation, there's still a lot of exciting room to grow and improve. And this brings to the end of my presentation. Thank you so much for your attention and time. And I really enjoy exploring the tensor diffusion network and its potential and multimodal sentiment analysis. So here it is, the end of it. Thank you very much.